So while I don't consider this to be a definitive proof video, um, I'm adding it to the Making Connections to and Within Simulation Reality series. What I want to show you is a methodology, and it's going to put us in the ballpark of how big the sun is and how far away it is from us. It's not going to give us the exact measurements, but it's going to be close. And with your help, with more footage, and more people studying and analyzing this, people that have AutoCAD skills, more people recording, getting better footage than I have, we will get a even more accurate idea of how big the sun is and how far it is in this video. But what you're going to see is that it's not 1,000 miles away, it's not 2,000, it's not 3,000 miles away, it's less than 10 miles away. What I'm going to do right now is I'm going to share with you a clip from a video that was shared with me by a commenter. This is somebody in the UK that was filming clouds behind the sun, but he also caught a bird flying behind the sun. And to me, this is one of the best examples I've seen of a bird flying through the sun. You can clearly see that the bird was behind the sun, and when it gets to the edge of the disk of the sun, it disappears because it's behind it, but then it flies through the sun. It comes out on the surface of the sun where it's still within the disk of the sun and is clearly visible. Now this clip is clear evidence that it's not the brightness of the sun that's obscuring the view of the bird, because it disappears, yeah, that's when it's behind the sun, but when it comes out through the face of the sun, it's clearly visible on the disk. So I'm going to start banning people that suggest that this is just the brightness of the sun that's obscuring our ability to see something. That is not the case, and this is evidence of it. So I'm going to let this clip run. It's 2.3 seconds. You'll probably miss it at first, and then I'm going to run it at 1/10 speed afterwards so that you can see it real clearly. So the reason why I took you through all that bird footage is to establish that we have something right at the distance of the sun and something measurable. So let me show you what we're going to do with this picture, the still shot. I've imported it into SketchUp, and the reason why I chose this picture is because the bird had just come through the sun, so we know it's right at the distance of the sun, and its wings are fully spread out here, so we're going to get a wingspan. So I'm going to take the rectangle tool, and I'm going to go from the tip of the wing here to the tip of the wing here, and that's going to be our measuring instrument now. So I'm going to take that box, I'm going to move it out to the diameter of the sun right here. I'll make some copies of it. And I'm just going to make 30 more of these. And now let's count them up. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 26 and a half. That looks like it's just about a half there. So we're 26 and a half birds wide. So what bird are we dealing with? Well, I'm at Wikipedia at List of Birds of Texas, and we have the golden eagle, and I live on a river here, and the other side of the river is the low side that floods out, and so it's unbuilt, and that is the direction that I'm looking at the sun. It's the golden eagle. Now I see these things land in my trees, they sit on fence posts. These are big, awesome birds, and they just soar around super high in the sky and I don't know, just float in the wind. So, how big is the wingspan of the eagle? Well, from 5 foot 11 inches to 7 foot 8 inches. So let's figure this out. But before we do the math, I just want to show you something really cool about the eagles. Their flight physiology. So this is a really interesting paragraph here, but it shows that the typical unhurried soaring speed is about 28 to 32 miles per hour. When hunting, it attains speeds of 120 miles per hour. And in a full stoop, it reaches spectacular speeds of up to 150 to 200 miles per hour. So it places the golden eagle as one of the 2 fastest moving living animals on Earth. So let's do the math now. So on this still image, I've noted that the sun is 26 and a half golden eagles wide. And from Wikipedia, we learned that on the small side, the wingspan of the golden eagle was 5 foot 11, which is 71 inches. So 71 times 26.5, that's in inches. So we're going to divide that by 12. So on the small side, we have a sun of 156.8 feet. And then on the large side, it was 7 foot 8, which is 92 inches. So 92 times 26.5, that's in inches. We're going to divide by 12. So we have a range from 156.8 to 203.2. So I've just put a notation on our still image here of 156.8 to 203.2 feet. Now let me show you, there's another way to verify this. So let me show you that. So I've been noticing a big push from the popular flat earth channels that are promoting the sun and moon doing circles over some sort of an AE map. they've been promoting the idea of an apparent sun. They've been talking about how there's just no possible way that we can measure the distance to the sun or the size of the sun because, it's apparent. Light refraction, all these different things are reasons why we can't measure it. But I don't believe that at all. I think that's all disinfo. I think they're out to deceive us. Um, the angular diameter is something that navigators have used for a long time. They've used sextants. And so here we are at Wikipedia under angular diameter. And you can read all these formulas and brush yourself up on all that stuff. But this table shows the angular sizes of noteworthy celestial bodies as seen from Earth. And here's the sun. Now, if we scroll down a little bit further, it says the table shows that the angular diameter of the sun when seen from Earth is approximately 32 arc minutes, 1,920 arc seconds, or 0.53 degrees. So let me show you what I got going on here. This is SketchUp again, and I've got 3 circles. 1, 2, 3. And these are the radiuses, 26,400 feet or 5 miles, 39,600 feet or 7.5 miles, or 52,800 feet or 10 miles. So I'll just show you here quickly. You can see down in the corner, the length, just verifying all these things. So that is the size of our circles. Now what I want to do is grab the protractor, set it out here, and now I'm going to go 0.53 degrees. So this line right here is going to give us a distance at 5 miles. Now when it's blue like that, that means I'm following the vertical axes. At 5 miles, 0.53 degrees is 243 feet, 11 inches. At 7.5 miles, it's 365 feet, 10.5 inches. And at 10 miles, it's 487 feet, 10 inches. So you've heard me say it's less than 10 miles. Now, if we're going with the wingspan of the birds, it's less than 5 miles. Okay? But these are close. This corroborates each other. We're in the 200-foot range for a diameter of the sun. And we're less than 10 miles. We're probably about 5 miles. So I know 5 miles for a distance to the sun sounds very disprovable and absurd. But I want to be clear that what I'm talking about is for an observer on the ground, on relatively flat ground, where they're not viewing from an elevated position. So this picture right here is a little deceiving, but I'm at a distance to the horizon calculator. And we're going to put in an observation height of 5.5 feet, and the distance to the horizon is 2.9 miles. Now this picture you can tell is taken from an elevated position. What I'm talking about is a person standing on the ground. This horizon line right here, when viewed from 5.5 feet above the ground, is 2.9 miles. Now here we are looking at Google Images sunset from a beach, and we know that this water is flat, and that for the observer at 5.5 feet, that horizon line right there is 2.9 miles away. You can see when looking at these pictures And take a look at this. Those clouds are just 2.9 miles away. And so if the sun is setting uh, at 5 miles, if its distance is 5 miles from us, and because of its brightness, it's plenty far enough away so that from us, the observer, it it just gets hidden beyond the horizon. So what happens if you're viewing the sun from an elevated position? Well, I did a Google search of images for sunrise pictures taken from a mountain, and I like this picture right here because it tells us that it was taken at West Tetras National Park. So if we look at the Tetra National Park, this is in Slovakia, and it says under mountains here that the highest peak in Slovakia is 8,711 feet and is located within the park. So let's just say that this guy is at the top of this highest peak. At 8,711 feet, the distance to the horizon is 114.4 miles. So in this case, looking at the sun from an elevated position, it's not 5 miles away. It's maybe 116 miles away. So just far enough to be beyond the horizon line. So what about if we're viewing the sunrise or sunset from an airplane? Well, they typically cruise around 35,000 feet. And so here's a picture looking out the window. And at 35,000 feet, the distance to the horizon is 229.3 miles. So without these clouds in the way, if we're able to see all the land down here all the way out to the horizon, I mean, at that distance, it's just too far to see with a telescope. But let's say you could, the sun would be setting just beyond that. Or what about high altitude balloon footage? I mean, take a look at this image here. Now the sun's not at the horizon, but let's say this balloon is at 100,000 feet. Then the distance to the horizon would be 387.9 miles. So that would be, the mileage down here on Earth out to the horizon. And then if the sun was down here at the horizon, let's say our balloon was able to sit here and wait out the whole day. If the sun was just a couple miles beyond that and then made its path, and the balloon was there recording the whole time, all the way out to the other horizon, it just needs to be a couple miles beyond the distance of the horizon, and it all works. So why is it that flat earthers believe that the sun is 3,000 miles away? Well, I'm at a Flat Earth wiki article here on distance to the sun, and there's the mathematical way. Eratosthenes argued for a large distant sun using shadows, which also works for a close small sun as well. But the proof that I like best is the one from Zetetic Cosmogony. Thomas Winship writes, on March 21st through 22nd, the sun is directly overhead at the equator and appears 45 degrees above the horizon at 45 degrees north and south latitude. As the angle of sun above the earth at the equator is 90 degrees, while it is 45 degrees at 45 degrees north or south latitude, it follows that the angle at the sun between the vertical from the horizon and the line from the observers at 45 degrees north and south must also be 45 degrees. The result is two right-angled triangles with legs of equal length. The distance between the equator and the points at 45 degrees north or south is approximately 3,000 miles. Ergo, the sun would be an equal distance above the equator. And here we see a good description of what he is talking about. So, at a distance from the equator of 3,000 miles, we're at roughly 45 degrees north, same to the south, And by making that right triangle, we would assume that the sun is 3,000 miles high. Now let me take this and put it into SketchUp, model this up, and show you what it is that I'm seeing. So here I've got a map imported into SketchUp, and in my opinion, this is the best kind of map that we can be using. Not an AE map, but an actual just spread out flat map like this, and I'll show you why in just a second. But what I want to do is go over the Thomas Winship proof, which is a day on the equinox, how at 45 degrees north and south that the sun, the angle that it hits its solar noon, the declination is 45 degrees, and we know that the sun is directly over the equator. So if it's 3,000 miles from 45 degrees north to the equator, then the sun should be 3,000 miles high. I mean, that's what I was taught from the beginning, and it made sense to me. It didn't not make sense to me until I started filming clouds and birds behind the sun, and that really changed everything. So the way I see it is if we zoom in here, this isn't to scale, but it's a representation of, this is a 5-mile radius and a 10-mile diameter here. Now, once again, this is not to scale, but a person standing at 45 degrees south latitude, because the sun is going to have a 45-degree declination at solar noon, what they're going to see, and I can't really zoom in too far otherwise it blows out, but what they're going to see if they're looking to the west is the sun rise, and it's going to arc up till it's at a 45-degree angle here, and then it's going to come back around and it's going to set, 270 degrees west, and it rose 90 degrees east. A person at the equator is going to see the sun rise 90 degrees east, set 270 degrees west, but their solar noon is going to have the sun directly overhead. And then, it's just the opposite for the north. I'll go up here and take a look at it quick. You can see the same type of setup. The difference between what Thomas Winship is saying with a 3,000-mile high sun and what I'm suggesting is that we can only see a very short distance, if we're on the ground, 2.9 miles to the horizon, and we're filming clouds behind the sun, birds behind the sun. Okay, so what we're seeing is just this small bubble here. Now, it begs the question, well, how does everybody see it? So let me show you that quick. All right, so what I've done here is I've just taken what we had before and I've copied it and spread it out across the whole map. And so we're talking about the equinox, which has equal day length, 12 hours daylight, 12 hours nighttime. And what I believe is happening is that at the beginning here, based on where you are on the map, your day begins at a certain time and ends at a certain time. So as you come along here, your day is going to, begin just a little bit farther behind, all the way across. For each location, the day is just going to, begin a little bit later, and then it's going to end. Begin a little bit later, and then it's going to end, all the way across here. And we typically think of this as time zones, but I think of it as your location triggering the beginning and ending of the day all the way along. Same with the equator. And same here at 45 degrees south. Now this is a representation for an equinox for me. Now I plan on modeling up how this looks for the winter solstice and the summer solstice as well. And then we can do it at various locations. But what you're going to see is that all these sunrise and sunset angles in the northern hemisphere and the southern hemisphere. So when the sun is south of the equator, you're going to have a lower angle here and a higher angle here. And then when the sun is north of the equator, you're going to have the higher angle here and the lower angle here. And we're going to model it up for each of these times, and we're going to do it for different latitudes. And I believe that as you see it more and more, and as we film birds and clouds behind the sun more and more, I believe this is going to make sense to people. Now for calculating the speed of the sun, let me show you what I'm doing here. This is to scale. So let me show you quick. We've got a diameter of 52,800 feet or 10 miles. And we got a little person here at the center, at the origin. So here we are. This is to scale. This would be a sunrise at 45 degrees north on the equinox. And so let me show you what this looks like for this person. I'm going to position the camera here. And so they would see the sunrise. Could see solar noon at 45 degrees. And they would see the sunset at 270 degrees west here. Now let's come back out a little bit. And I'm going to show you the length of this arc. We've got 82,466 feet. So let's bring up the calculator. 82,466 divided by 5,280 feet in a mile gives us a distance traveled of 15.61. Now this is the equinox, which is a 12-hour day. So we're going to divide this by 12. And we have a speed of 1.3 miles per hour. So that distance traveled is the speed of the sun. Now this is for a person that's standing still right here, because this space is always going to stay in relation to where you are. So if you stood there on the equinox and watched from sunrise to sunset, you would see the sun traveling about 1.3 miles per hour across this 10-mile diameter space. Now keep in mind, what we did is we just calculated the speed of the sun for an observer that's at ground level, where they're looking from 5.5 feet above the ground. We were talking about a 10-mile diameter viewing distance. So I'm at Google and looking at the world's tallest observation deck. And in Dubai, the tallest observation deck is at 1,823 feet off the ground. So 1,823 feet gives a distance to the horizon of 52.3 miles. Now what I'm going to do is I'm going to add another 2 miles to this so that the sun goes down below the horizon, behind the horizon. So I'm going to use the figure 54.3. So using the same technique, I have a radius here of 54.3 miles, or a diameter of 108.6. And now if we check this arc, we come up with a length of 900,707 feet. So let's bring up the calculator. 900,707 feet divided by 5,280 feet in a mile gives us 170.58 miles traveled by the sun when we're viewing from that type of elevation. Now in a day on the equinox where it's 12 hours long, we'll divide this by 12, and now we have a speed of the sun of 14.21 traveling that arc. So our elevation affects the speed of the sun because we have this longer distance that we view things out to the horizon. If you're in an airplane that was even higher, and we have this larger distance out to the horizon, then the speed of the sun would be larger even yet, or faster even yet. So that's the reason why people are getting these different speeds for the sun. It has to do with the elevation. They're making the mistake that they're plotting lines, based on the sunrise and sunset angles or the solar noon declination angles. They're plotting these lines out and assuming a physical sun that's going to be up here 3,000 miles away. When in actuality, we're in these bubbles here, and based on our elevation, we can only see things a certain distance away. That's the reason why we can see clouds behind the sun, birds flying through the sun. So this is a rough estimate of the speed, but it's a technique for figuring it out, and it's a whole lot closer than what we've been told. I just want to show you I'm at YouTube and put in the search clouds behind the sun, and we're getting about 293,000 results. Now, there's a lot of people that have footage other than me. Now, I've got a fair amount up there and you'll see that, but take a look at all these videos that show that my sunrise compilation in St. Martin is a bunch of sunrises that have clouds behind the suns and birds. Most people have not gone as far as to say that they see birds behind the sun, um, but I do. And you can look at these people's footage of clouds behind the suns, and they have it too. They just haven't gone that far. It's a big step. But go ahead and look through all these. You'll see a couple debunker videos. Check them out. Check it all out. And add to it. Make your own. We got clouds behind the sun. Now, I just want to show you, here's a debunker. And let me show you what some of these debunkers are doing. Look at this. You're going to see, oh, he put an overlay across the edge of the sun here so that you can't see the edge where the clouds are behind the sun. Well, what needed is there for an overlay right here, other than to hide the evidence? I mean, that's what the debunkers are doing. Look at that. You can see this is where the clouds are behind the sun. He had an overlay there. So look at all this. Clouds behind the sun. 293,000 results. I'd like to see that get up to the same amount of flat earth videos out there. Because this right here is a game changer as far as understanding our reality. Because then the sun's not 3,000 miles high. I mean, we already know that it's not 93 million miles away, but it's not 3,000 either. It's a simulation, and that's what I plan on showing you, and that's where I started now, but I'll keep going. So as we watch some footage of clouds behind the sun that I took, I just want to say once again, I do recognize that these calculations aren't exact. I was doing it in SketchUp. Um, I need people that know how to use CAD software and people that get better footage than I have to help out and to fine tune these results. But the methodology, the the premise I believe is correct. Now, if something comes along that shows me that I'm incorrect in this, I welcome it because I'll make a correction video and I want the truth. So finding out that I'm wrong about something is sort of exciting in a way because it means that I found something correct. As far as people that are going to say that it's the brightness of the sun that's obscuring uh, us being able to see the birds and clouds and stuff like that behind the sun, the evidence is all in this video and the thousands of other videos that people have taken that that's not the case. So I am going to ban people that say that because I do believe that they're detractors or just so stuck in a mindset that they're not going to help out. And I am, and I hope the people on my channel are looking for the truth. So thank you for watching. I've got at least 30 videos stuck in my head right now that I need to get out, and I'll do that as quick as possible. Thanks.